GPS denied environments are something that are of interest to you. And for us, and simply the indoor stuff that you presented, Somil, there was no GPS, so that was good as well. So I think that it's sort of a challenge problem that could be, and Mayur, I think that if it's, I think certainly when your folks were here, there was some interest in sort of using this as a framework to evolve, the software tools and so on and so forth as well. So that's, should we can have a little discussion after the presentation if that's, okay. Your guys are on. Okay. You're going to introduce who's presenting, right?
So the main presenters are still to be Jack and Franco.
Who you've seen before, so
I've been here. So we're gonna pick up essentially from where we stopped the last time. We introduced the whole perception stack and the whole concept of the competition. We got to the controls stage. We went over a couple of details of the starter controls, but I think it's good to start from the last checkpoint essentially, which is the starter controls, and so that's what we're going to be doing. For reference, in terms of controls, we've been developing a model predictive controller for integrated lateral stability with an extension to position tracking of autonomous race car. So just for clarification, this is purely a lateral stability controller with no longitudinal concern. We have a separate controller that is used for longitudinal control. In terms of this controller, our key specifications that we were looking for were that it operates in 3 degrees of freedom, which are lateral motion, yaw motion, and roll motion, sometimes called a rollable bicycle model. It essentially accounts for 4 wheels in the roll direction and some bicycle model simplifications in the plane direction. It relies on a dog-off tire model, which is linearized at every MPC iteration. And I'm going to get into the details of why this is done in a couple of slides. And the third point is that because this is a problem that we're solving for an autonomous race car. However, we want this to be like a universal solution. And so we want it to work for any vehicle that we have. And so we included an actuator configuration matrix, which essentially accommodates for available actuators in terms of if we can have like split differentials, if we can have rear-wheel steering, everything's accounted for in this controller. Quick, before I get started, the inspiration behind this work is the paper mentioned at the bottom of the screen. In fact, it set up the backbone and then we applied the modifications that we needed for an autonomous race car and what follows. Okay, so let me get started. First of all, why we need a controller. There are 2 cases of kind of a vehicle not operating the way you want it to. We have a case for oversteer and a case for understeer. Understeer is when the car does not go where you want it to go because it steers less than you want it to, and oversteer is when it steers more than you want it to. And essentially understeer is very controllable because if you're understeering, you can hit the brakes, you can increase your steering angle, you can still, as a driver, control for it, but when a vehicle is oversteering, that's when the problems arise. Because when you enter the oversteer region, it's very difficult to control the vehicle unless you're a professional race car driver. So essentially what our controller is trying to do is it's trying to avoid the oversteer situations and control the understeer situations. All right, so an outline of how this is going to be structured. I'm going to start with the literature review, why we chose what we chose, and then I'm going to step into the problem dynamics as defined by the paper inspiring this work, control objectives and results, and then and constraints, and then finally get into some simulation results. After that, I'm going to speak about how we extended this problem to an autonomous race car particularly, and mention some simulation and results on that front. All right, so in terms of literature review, the first choice is to select what kind of control scheme we're going to be using, and we selected model predictive control based on 4 main reasons. The first one being the need to accommodate for stability constraints. Essentially, in terms of optimal control, you could use a linear quadratic regulator. However, that one would not account for keeping the vehicle in the limits of stability. And so this one kind of knocked down some options that cannot accommodate constraints. In terms of the second main point, it's accounting for a multiple input, multiple output system. So this is an autonomous racing car, which is a very complex system. It has all of its states that are kind of fed back into the system, forces, and as outputs, we're going to output steering angle. And so the multiple input, multiple output nature meant that we cannot use some very conventional schemes that would decouple our dynamics, such as PID control. Moving on to the third point, and the most important point, is the predictive nature of the controller, whereby it could, based on a roughly kind of accurate mathematical model, it can look further into the future. The time that we've set is 1 or 2 seconds, and it can just see if it's going to be stable at that point in time based on an input that's provided at this point in time. And so that's kind of very pivotal thing that we were looking for. And finally, the fourth point is essentially the ability to tailor for the performance index through weight tuning. And the point of this is essentially we can put weights on how good we want the tracking to be versus how stable we want the vehicle to be, and essentially kind of compromise the two in order to ensure that the vehicle is always stable even at higher speeds. So after we have selected model predictive control based on these 4 points, we move into what the different models from MPC were based on. And the 3 points they were based on were the ability to capture the dynamics and the aforementioned degrees of freedom I mentioned on the previous slide. It's also based on the implications of the complexity of the model in terms of compute time, because we wanted to run in real time, of course, as Professor Sastry mentioned earlier. And the last point is, in terms of the tire model used, we want it to be a fairly complex tire model, but it still needs to run in real time. So this kind of reflects on the 2 points above it. So let me move into the tire model and what we ended up using. Essentially, we ended up using a linearized dog-off tire model. And the main reason for that is if you look at the conventional dog-off tire model, it's the one shown on the left. It captures dynamics fairly well. However, it's extremely complex. And if you look at the variable that we work with, which is alpha, it's kind of extremely nonlinear in alpha. And so in order to accommodate for that problem, what we do is essentially we linearize this model based on a hard-coded, essentially, linearization function that takes us from the function on the left-hand side to that on the right-hand side, which is a very linear, very nice function of alpha. We do this every 100 milliseconds. So kind of we're not linearizing over the whole MPC horizon. We're doing this every single iteration. And so this kind of accounts for the complexity and the time complexity and the model complexity factors of this problem. All right, so that's for tire dynamics. If you move into the vehicle body dynamics, they're derived from So we move into the vehicle body dynamics, and essentially these are derived from Newton's second law. It relies on, as I said, in plane with rule dynamics, and it relies on the stiffness and damping of the overall vehicle. The wheel dynamics are considered in this case, and this is the case for the general electric vehicle. Also, with the problems defined in terms of U, which is the change in inputs, so it's the vector shown at the bottom, which is the change in wheel torque, change in steering angle for every single wheel. And hence, based on the actuator configuration matrix, we can control which ones of these we can use actually to control the vehicle. Ultimately, the resulting model that we get from Newton's second law is the one shown on the top, this one right here, where we have a state space model with input F, which are the forces in the longitudinal, the lateral, and the yaw direction. We can also see that the model that we would like to have is one where the inputs are the changes in steering angle and torque, because that's what we can actually control for. We cannot actually control for forces. So to get from red point to black point, what we do is we go over some math, a lot of math. And basically how that goes is essentially we start with our linearized tire model. And from that, we use the following equation, which is the relationship between the slip angle, the steering, so it's the slip angle of the tire with the steering angle, the lateral velocity, the longitudinal velocity, AI, which is defined as the distance from the center of gravity to the front axle, or the negative of the distance from the rear axle to the center of gravity, and the yaw rate. And essentially by doing this, we can move from the left-hand side to the right-hand side, where we have our tire forces in terms of our vehicle body states. After doing this, we can then use a mapping matrix, LWI, which we use to move from the forces on the tire to the forces at the corners of the vehicle, which are essentially this, like the rotation of the forces on the tire to the direction the vehicle is pointing in. We also here add the control input as the fourth term over here. After doing this, we can then take these matrices, these 2x1 vectors, and we can put them all on top of each other, and we get this kind of simpler notation. And after that, we can use the following matrix, which is called LC, which maps all of our forces from the corners to the center of gravity of the vehicle. And now we have F, which is the force in the longitudinal, lateral, and yaw direction, which we wanted in the previous slide to substitute for. So now we substitute all of this backwards and into the model that was on the previous page, and we can finally get a state space model represented in terms of our inputs. In terms of our wheel dynamics, we can also get those from this simple equation for wheel dynamics. We do that for every wheel, and then we can concatenate those vectors on top of each other and get XW dot. After doing this, again, we take these and put them on top of each other because we kind of like to do that. And we can get the following state space model in terms of our inputs. All of the matrices shown in this model are shown on the right-hand side. They look a little bit complicated, but essentially they could be coded by easy matrix multiplications. Our states here are shown by this vector and our inputs are shown by the one below it. So after being able to derive a model, now we're working a little bit more with the controls, and it's essentially what are our constraints and what are our costs. So for any vehicle, our main constraints are going to be to try for the yaw rate to be within the limits allowed by the tire road coefficient of friction, and essentially this is like limiting the yaw rate within the allowable bounds, because if you go beyond those, your vehicle is going to slip out of control. We also have our rollover index constraints, which is made for the vehicle not to roll over. The maximum allowable wheel slip ratio, which is essentially for the tires not to burn out in their own location. We also have the rear wheel slip angles, and the reason we care about the rear wheel slip angles is the understeer reason that I mentioned earlier. So if the rear wheels slip out, that's when oversteer happens, whereas when the front wheels slip out, that's when understeer happens. So we care about the rear ones more than we care about the front ones for stability. We also have the maximum and minimum wheel torques. Those are based on the actuator capabilities. We have our friction circle constraints, our maximum steering wheel angle, again based on actuator constraints, and finally our vehicle dynamics. In terms of costs, the first and foremost cost is to track the desired yaw rate. We want to track it as closely as possible. However, we also have a cost that's kind of conflicting, which is minimizing the lateral velocity, essentially the vehicle slipping out of control. The remainder of the costs are of lower importance, which are essentially minimizing the roll angle, roll rate, and ensuring the tire speeds track the long-term velocity. All right, so at this point, we got to this point, and then the simulator we were using ran out of, was sunsetted, so we had nowhere to test this. So what we had to do was we had to develop kind of a makeshift simulator, a low fidelity simulator, in order to run our controller on, test it, see if it works with model error and so on. So what we did is essentially we used a kind of a bicycle model simulator that we made based on the following equations for the tire forces. And then we also updated the torque and steering angles based on the optimal values from the previous MC iteration. We also used perfect model knowledge to start with, and then we started applying some kind of noise to see if the controller still functions, if it's getting wrong inputs. The results were kind of pretty. We were operating on an MPC horizon of 10 steps and a sampling time of 0.1 seconds, and we simulated the problem for 25 seconds. And essentially here we were running with a vehicle speed of 80 kilometers per hour at a steering angle of 0.15 radians. The parameters used here were those of a Mercedes E-Class, just to provide preliminary testing. And as you can see, we can almost track the yaw rate perfectly. The reason we don't go up to that value is because this is beyond the stability limits as defined by the tire road coefficient of friction and the vehicle parameters. In this case, the only available actuator we were using were the wheel motors. So we assumed that, let's say the steering wheel is broken or something. So can the vehicle actually regulate itself? And indeed, we can see that it does that through controlling for the wheel speeds at the individual wheels. So we can see that the left wheels are slower than the right wheels, which means that the vehicle pivots to the left-hand side. Okay, so that was it for the general problem. Now, what do we change when we want to work with an autonomous racing car? The first and foremost point that we need to change is essentially including the road banking angle, because when we're operating, especially on an oval, our banking angles go up to like 20 degrees. So we need to account for that, and we need to have that inside our model. The second point being stiffness and damping, we wanted to consider those for the 4 shock absorbers instead of being for the whole vehicle. The reason for that is because that's what we have access to based on previous experimental testing. And so we wanted to use those instead of having to run new experiments. And the final point was state vector changes, and those are as seen here. So as you can see, we remove the wheel speeds because we already have a longitudinal controller, so we don't need to have longitudinal aspects accounted for here because we can't control for them. And we add a state, which is Y, which is what we're trying to track the lateral position in this case. As you can see, the changes in the body state vector are mainly reflected in terms of the addition of a C phi R, which is essentially the contribution of the banking angle to our vehicle body dynamics. And just for clarification, given the nature of the car that we're using here, the actuator configuration matrix is selected such that it turns off the individual wheel speed control, and it only activates control for the front wheel steering angle and makes sure that the inner and the outer wheel have the same steering angle, because that's essentially the case we're working with. All right, so let me move into a little bit of details. Sometimes with race cars, you do go into oversteer conditions. As you can see in this case, in 2012, I believe, Michael Schumacher in Monaco, you can see that the vehicle actually skids out of control, but the race car driver is still able to control it and still able to maintain, to go back to a stable region despite leaving it. So essentially, this is what kind of performance we're looking for in terms of oversteer conditions if the vehicle were ever to go into those. All right. So based on that, we had to change our control objectives and constraints a little bit. Namely, the grayed out ones are the ones that were removed from the previous case, and those are essentially accounting for rollover because that doesn't matter in the case of a race car. It's not going to roll over. I could say with fair confidence. And the slip ratios are no longer so anything related to longitudinal dynamics is removed. This being a purely lateral controller. In terms of costs, of course, we had to drop the costs a lot on roll angle and roll rate for the reasons I mentioned earlier. And we had to place a very high cost on tracking the lateral position because now that's our main concern here, so that we do not run into walls, into other cars, and so on.
Can I interrupt and ask a quick question?
Yeah, sure.
So to me, it seems like the relative weight between these cost terms will depend heavily on exactly what scenario you are handling at the moment. Meaning, are you sort of near oversteer conditions versus you're just like, I guess, driving on relatively straight curve.
Yeah.
And at least in my experience working with multi-objective MPC problems in the past, like that significantly affects the performance of these algorithms. Is that something that you observe in your work? And if so, like what are general strategies your team take to handle those situations?
Yeah, that's actually an excellent question. So as of recently, we were able to spot a kind of a correlation between how big the lateral error is and how the controller performs. So at bigger lateral errors, that's when the car tries aggressively to steer into position, and hence that's when it starts to oversteer. So kind of the approach that we've been using essentially is to have like a kind of a dynamically changing weight that varies, weight in the cost function for these first two especially, that varies based on essentially how close you are to the checkpoint. The farther you are to the checkpoint, the more you drop this weight. And the reason for that is to avoid going into an oversteer condition. Interesting.
Yeah, that's very exciting. I think the one thing I was just thinking on that front, we can discuss, once you are done with the presentation, is that could be another really good use case of learning in this system.
Absolutely.
So just about the learning story there, and I haven't probably. But they say that these drivers, when they drive these courses before the trials, before they drive it, a lot of what they learn is really this game of inches about where exactly they sort of learning the optimal line for taking these curves. And I presume that's so that if you were to call that sort of the learning part for the way you balance the maybe the propensity to not get into an oversteer or something like that with because so apparently I've heard it said that after the race is done, they take a look at where the tire marks are. Yeah, and the tire marks are always like within a few inches, like nobody deviates because if you do, then you're basically dead after years. Somebody overtakes you or something like that. So is that a plain thing to bring learning to bear on, or?
I think it would be a very interesting application in this situation because then again, like in terms of what I'm trying to do at the moment, it's trying to emulate something that can get as close to an optimal solution as possible. But I think the opportunities for learning here are
well, see, I think that's what Somil would do. He'd sit on top of this. That's to put words in your head and to get the exact line, for the.
Absolutely. No, definitely.
Yeah. So I don't want to derail, but we can chat offline. I think that could be a really good use case.
Absolutely. I do agree. I would love to chat about this after this presentation. Yeah. Okay. Lovely. Any other questions? All right, good. I'll go through then, I guess. In terms of now, this is like the objectives of the problem. In terms of formulating it to make sure it's as quick as possible, we had two kind of formulations. They were both made in Python. The first one was essentially just using Pyomo and imposing every equality and inequality constraint separately. And this was done for prototyping. This is not the most efficient algorithm, but it's the quickest to make. So we just made it preliminarily to test this MPC and make sure it essentially runs and works conceptually. And then after that, we were able to construct this as a quadratically constrained quadratic program with substitution and implementation in Casati, with a vision to translate this into C++ to run it even quicker in the future. As of currently, it's been running at a pretty decent speed. It essentially has one big matrix constraint and one quadratic cost function.
Can you just elaborate what Pyomo and Casati are?
Yeah, so they're essentially optimization environments, and Pyomo is kind of it's a really slow one that's essentially used by beginners, just so you can essentially put everything in there very easily, and it's easy to formulate and whatnot. In Casati, it's a little
what
bit.
kind of optimization are you doing there?
It's quadratic optimization, essentially, a quadratically constrained quadratic program. So this one's really quick to work with. Casati has kind of some quirks to it in terms of how you formulate the problem in order to make it run quickly. It also has a lot much quicker solvers. So that's why we shifted into this one. Yeah.
And if I understand correctly, the MPC problem that we're trying to solve, is that more like a robust MPC problem, because you have both control and there was some D and W, which I'm assuming were some sort of noise or disturbance? Is that how we're modeling?
Oh, no. So essentially, let me go back to that slide for a second. Yeah, so the D matrix here is essentially, it stems based on the linearization that we spoke about, because you have some constant terms and they're all thrown into this D matrix. The W matrix is essentially, so we said U is the change in inputs, the change in steering angle. So W sets the start point. So it's essentially where your steering angle starts at, and then you can account for what U is changing.
Got it.
Yeah.
Sorry, I got confused by those notations.
Yeah, yeah.
Those are for noise and disturbance in control theory.
Yeah, no noise and disturbance in this case.
Thank you for clarifying.
All right, so following this, then again, at this point, no simulator, so we had to run it on a low fidelity simulator. And in this case, we're running an MPC horizon of 50 steps, which is a pretty long horizon, a step time of 0.05 seconds and a vehicle speed of 108 kilometers per hour. And essentially, we're trying to emulate an overtaking maneuver. Don't let the XCs fool you. This is 3 meters in the lateral direction and 350 in the longitudinal direction. And so essentially, we tried it with a bank angle with 5% state error in terms of noise. We tried it with a perfect model. And in all cases, you can see that the MC is able to perform the moving out and then moving back in at the proper angles in order to stay in line. This is on a straight, which is where most of our overtakes tend to take place, which was pretty promising at this point. However, as of recently, we were actually able to gain access to a high fidelity simulator. And this is not a high, it's in a couple of slides, I'll get there, sorry, got excited. So in terms of tire loads, when we have a banking angle, we can just see the load shift into the inner tires, which is kind of expected. In terms of like the other cases with state error, and in the case of a perfect model, we can see the load shift between the left and the right tires. However, there are some oscillations in the perfect model case. We consider them to be insignificant as they have very low peaks, but the MPC could be further tuned in order to remove these. Last point is that in terms of tire slip angles, we just wanted to check for those, make sure that the MPC is always feasible, because it's running for a long time, so we can't go through every line of code. So we can clearly see that the MPC remains within the stability limits for its rear wheel and front wheel slip angles, which is very promising in this case, because we're running at higher speeds in this case, like 108 kilometers per hour. So yeah. All right, so yeah, this is the part I was excited for. Now, this is not a very high quality video for
simulated at low speeds, because you're actually going to run this
at higher speeds.
Yeah,
because this is a low fidelity simulator, so it's not very representative of what we're going to be running in real life. So that's why we started with essentially the lower speeds, just to capture bugs inside the MPC essentially. Okay, let's see, is this one? Oops.
is it because of this Zoom and your player?
I think that's what's happening, because it wasn't happening before now.
Yeah, quite that's it.
Okay, there we go. So yeah, it's a little bit. Does it work again? No.
No, you have
I'll have to see. Yeah. So essentially, this is like it has horrible quality, this video, I'm sorry about that, but it's essentially it shows how the vehicle can actually track the racing line. In fact, here we were operating within, like, our lateral error was about 5 centimeters, which was very promising. This is around the Las Vegas track. Still pending further tuning where we actually can operate at all kinds of speeds, all kinds of places, but nonetheless have been very promising as to this end.
The take-home message is that we have a working system.
We have a
Nobody
absolutely.
should.
Yeah, absolutely.
What can you change in the simulator as far as the environment configuration? Track,
Yeah, we can change the track.
just tell us what that means. Like, can you change the surface characteristics? Is the track just like an open track with nothing else on it? No other?
Yes, so we can run it with a track with another car on it. We can change the tracks in terms of like all the surface options, everything like that. We can modify all of those. We can change the actual track layout. It's essentially, there's a lot of flexibility in terms of what you can do on this simulator. Yeah.
But for the simulations you've done so far, you've set it to some particular thing.
Yeah, we've been running with a single car and minimum grip, essentially is the case we've been running for. So it's like a worst case kind of scenario in terms of grip and just one vehicle and testing that out.
Why don't you talk about Monza? So
I'm waiting for the board. We're gonna be up for that, so I'm gonna keep that for them. Okay. Yeah, so let me hop into like just some final quick conclusions. What we have right now is we have a multi-predictive controller for a general electric vehicle and another one for an autonomous race car. Essentially the same one, but just like small tweaks in each of them. Some practical implementation considerations that we've made. We developed a Kalman filter that actually could estimate tire friction coefficient. And this is more for a real-time implementation in actual.
hey, so that's great. So let me, wonderful presentation, don't get me wrong. But I think one of the things we had charged about doing in this program is to develop the software toolkit so as to make it more pain. That's why Sanjit's asking these questions.
Yeah.
So what can we do with the tools that you have developed? And
The critical part is the simulator. Without a simulator,
you need a better simulator. So
yeah, Kala is not going to be enough.
Kala is not enough.
Yeah,
And why is it? This will be a stupid
because the
question.
Kala does not, Kala itself does not have a customized vehicle dynamics model.
But this simulator is what?
LGSVL.
It's
Oh,
from LG.
Yeah.
What is LGSPR?
It's LG Silicon Valley Lab.
Yeah.
We worked with them in the past.
Yeah.
We actually have our tools interface to a previous version of LGSPL.
Yeah.
Do you do?
But they sunset that
So
project.
Scenic, our tools are interfaced to LGSPL, and Eddie was involved.
They
in that.
lay off the entire team last year.
But that's right, exactly. So
Yeah.
LGSPL essentially closed down that effort. But you're saying that they have a reasonable dynamics model?
Yeah.
But what are you going to do going forward? So we're GSPL, Carla is not good enough.
It's open source.
LGSPL has been open source,
It's
so I
open
guess
source,
there's a community.
but
of
there's no
people
support.
using it.
There's no support. So
Right.
you're on your own.
So unless we want to take, if you want to, take over the baton,
No, but what, we want to do the design tools. We don't want to build a new simulator.
That's right. No, I mean, I think we could, so given that at least my group's tools were interfaced to LGSVL in the past,
Yeah.
we could
Yeah.
essentially try checking if that interface works for this particular instantiation of the simulator. And that essentially what we'd be able to do is run through, essentially you can think of it as accelerated testing in all possible configurations of your FPC controller.
That would be amazing. That would be amazing.
These guys, sorry, this is Alan's punchline. Whatever we can do so that the maximally painless,
Yeah.
they only get the car a few weeks before the race. Right, so whatever,
And you want to design.
minimum tweaking that they can do there.
Okay,
That's the difference between winning and losing.
okay.
So if our design tools can really cut down on that last minute tweaking.
Right.
And so if we provide sort of a tool chain, and then in terms of conceptual matters, that's the goal of verification. They call that the validation phase. So it's the verification to take the pressure off the validation.
Using the verifier to do, well, not only design tuning, but also experiment design for the few weeks that you have on the track. Right? You want to be able to run the right tests.
Yeah.
Right.
So,
And then so that you tell them, the verifier goes this far, but now you test it on these other scenarios and then tweak it and you're on your own.
Yeah.
So I think if we did all of that, it really feeds into the development and it is their single need. Single largest need.
And then we have
They want to do it as much, doing the virtual stuff is really the single biggest need. And that's why I think it really.
And then we have 5 other teams to really show that whether, the simulation works or not.
Yeah.
Now, Shankar, I want to give you some bad news. For Monza, it's not several days, it's several nights.
Okay.
Because of the Monza track is so expensive, so we don't even get full days access. I mean, in Vegas, these people spend the Christmas and New Year over there, but it's a good experience because they get like weeks, one week. But for Monza, it's going to be a few nights. We don't even get a full day.
When is that happening?
June 16th to
17th and 18th.
Before June 16th, 18th, we only get sporadic few nights to test the track. It's even worse.
Do you have the Monza track modeled in the simulator?
You don't even further bad news. Go.
Yeah.
There's gonna be your stories.
I think it's a good time to hand off to these people so they can tell you about more details about.
So let's
Talk about that.
continue with the reinforcement.
15
learning.
minutes. Yeah.
Yeah, okay. So what we do is
Go ahead. Just keep going.
we want to develop end-to-end reinforcement learning agent to control an electric car with throttle, steering, and braking for car racing in simulator. So our main contribution is to construct a racetrack in simulator, generate occupancy grid map as input, design reward function and action space, and convert action to control. So begin with, so since for Kala, there is no car racing map in the simulator. So we build a lot of map. And also we develop the vehicle dynamic model and put the sensor on the map, sensor on the car. So you can see on the right, it is our first map, which is the Berkeley minor map. It consists of 4 roads around Berkeley, which is the first map we did train the race on. And then we developed the second map, which is the Berkeley major map. You can see on the left, it is the Berkeley minor map. However, on the right, it goes up to the mountain with steep slope, sharp turns, and 5 times larger. And then we have 4 racetrack built in the simulator, which are EV Grand Prix, Monza Racetrack, Texas Motor Speedway, and Las Vegas Motor Speedway.
So in the Monza, because we cannot go there, Shankar, I want to just add it here, is that we just go to Google Map and then we get the GPS coordinate as raw as possible. That's the best we can do. And then we are approximating Monza as flat. We know that they are banging angles and then they are not in the same height, but that's the best we can do. So we grab the GPS coordinate on high resolution Google Map and then we build one. But it's completely flat. It's not a real model.
Yeah, so it is just an approach to get a similar one. So after we have the simulator, we are going to use reinforcement learning. So here is the recap for that.
Yeah, so in RL, an agent reacts within the environment through actions. So actions can be like steering and then braking of the vehicle, and then the environment can be an actual race car, or it can be put in the simulator. So each time an agent performs an action, it gets a reward and a state returned by the environment. The state can be something that the camera captures on the race car, and the reward is a logic that we previously defined based on the state we receive. And in theory, reinforcement learning is the only field in machine learning that can achieve real intelligent systems that learn to make their own decisions without human supervision. However, this is not possible today. But let's continue. The essence of RL is basically recording down a table. Let's say this robot tries to can either go left, up, down, or right in this little grid map. And then each time it receives electricity, it gets a positive reward. And each time it goes to the bomb, it receives a negative reward. So it's encouraged to get electricity and try to avoid bombs. So what it will do is through its experience exploring this little grid map, it will record average reward of each action in each different locations. So this is a very basic model of how traditional reinforcement learning works. However, if we extend this training scenario to our Carla map, the action space and the state space is just too big. We received 24 by 24 pixels, 9 channels, continuous image as an input. That's our occupancy grid map. And then we're outputting 2 continuous actions for actually 3 for steering, braking, and then throttling. So for each continuous axis, we have exponential increase in complexity, and it's impossible for the car to experience every possible occupancy map layouts. So it has to generalize so that when it sees enough of some occupancy grid maps, maybe it will, we're hoping that it will recognize pixels as edge of the roads that it cannot drive through. Yeah.
So for the people who have already taken the reinforcement learning class, I think that driving like teach a car to drive with reinforcement learning is easy. However, we spend 1 year overcoming failures for a reasonable conversion rate. So here I will introduce some of the failure cases. For example, for the observation design, since the observation here in the last page here is too large, we make an occupancy grid map, which consists of obstacles, vehicles, and as information of the input we get from the simulator. And since there is only 1 reward at the end, which have the score for how long you finish the lap, we manually add the reward line here on the second column to show the reward that we'll get when it crosses the reward line. Since it cannot read the speed of itself, we make 4 consecutive 4 frames for the model to learn the speed of the car. However, after that, we
Can you
found
just go back and
yes.
Explain what you mean by manually add reward line?
Yes, so those reward lines are not provided by the simulator, but we manually design the reward line for the car to follow. For example, to let the car.
By saying reward line just mean like waypoints.
Waypoints. Yeah.
Okay.
Waypoints.
So when vehicle passes one of the reward lines,
It gets
it gets a
reward. You
reward.
gotta kind of
Yes.
say break that
Exactly.
down.
Yes. However, for that version, the occupancy grid map is still not perfect. For example, at the beginning, we designed a Gaussian reward line, which you can see on the top, as to encourage the car to drive in the middle of the road. So if the car cross the reward line in the middle, it will get a higher reward. However, after training, we found that the car can drive better in the early stage. However, it's harder for the car to find the racing line in the future. So we changed that back to the uniform reward line. And also we found that the simulation FPS is too low. So we decreased the size from 84 by 84 to 24 by 24. But this will cause another problem, which there is no enough vision to see the turn, which is in the near future. So we have a larger view with 1 time, 2 times, 4 times, and 8 times of the map. And we resize it to 24 by 24 so that the car can see what is going on in the future. And also you can see that for this version, there is some duplicated information. So we only let the vehicle frame to have 4 frames. At the end, we have only 9 channels for the input of the racing movement. After we done with the input, we deal with the behavior of the car. So we might find that the car is stalling because it is pressing the brake so hard for a long time. And so we decide to terminate that when the stalling happens. Also, you can see on the right, the car learns to turn around on a straight road and then going all the way when there is no reward lines to reward it. And we also decided to terminate this actions. And also, you can see on the right bottom, this graph, the car learns to kill itself in the very early stage because it learns that the hot water penalty is too large. So it decides to crush itself at the very beginning. So we need to tune the hot water penalty to be lower and increase the crushing penalty. After we deal with the behavior, we have a very good result. Then we switch to the Berkeley major map. And since it is a more compact map with steep slope, larger map, and also sharp turns, the car learns to overfit the initial section of the track while cannot finish the lap. So we create many random spawning points for the car to learn all the different changes of the road. And also in the Berkeley major map, there are many steep slopes. So the car might fly in the air when it is driving so fast. And by adding the height to the input map, you can see here it is not 0 or 1. It is the height is encoded in the height map. So after put the height in the occupancy grid map, the car learns to drive straight when there is a large change in the slope.
You just train a stunt driver.
Yeah. So now the car can drive land easily.
Can I ask two very quick questions?
Yeah.
One is, could you tell me which RL algorithm you're using? And number two.
Oh, we are using PPO now.
Okay.
Which one?
Yeah, so
PPO.
do you have a slide?
Yes, we have
let's-
slides
yeah, let's-
later.
Yeah, let's go, if you can.
Yeah, we'll talk about that later. So
What was that flying thing? It was a car out of control, is it?
Because if you drive around the Grizzly Peak,
Oh, you were in the air.
yeah, there are bumps.
Yeah.
So these are not the things that, if you are
Wow.
a Tesla engineer, you will worry about, because if you drive on the highways are not allowed to have those bumps.
Yeah.
But in Berkeley, you have. So if you just apply the algorithm from reinforcement learning courses, then you're going to get a flying car. That's the problem.
And sorry, my second quick question is, are we training and testing in the same environment? That's what it seems, but I just wanted to confirm.
yes.
Okay.
Yes.
So overfitting is an option to RL in this case?
Yes, but we don't want overfitting in the early stage.
Got it.
And also we found that we choose different models to convert the action space into the control. For example, at the beginning, we test only let the model to control the steer, and while let the throttle to be fixed at 0.7. And also we tried the band control, which switch between full throttle and full brake, and so that the agent can control two different actions. However, for the band control, there's a problem that the output of PPO is continuous, but the band control is more like a binary thing. So the model will find a difficult time to learn it. At the end, we change back to the full control, which we have two continuous action space, one for steering and the second one for the throttle if it is larger than 0, and brake if it is smaller than 0. So for the whole structure, we have the first one, the simulator, which gives out the information we need to build an occupancy map on the second part, and take this as the input for the feature extraction on the third part. And after feature extraction, we feed into the RL agent, which is a PPO agent, to generate the action. And we convert the action to the control that feedback into the simulator. So you can see here is the stable steering only version. You can see the model can complete the Berkeley minor map in 1 million steps, but it can drive much better in 18 million steps with less wobbling. However, when the car learns to speed up, it needs to learn how to control the wobble every time it's increasing the speed. So in the future, we are trying to use the neural symbolic method to help the car learn the relationship between wobbling and the speed. You can see on the bottom right, it is the finishing time. And also another future work is we are trying to change from PPO to SAC.
Yeah, as we talked about, we're using PPO currently to learn how to control the vehicle. So basically how PPO works is it's an online reinforcement learning algorithm. So each time the vehicle performs an action and observes the world, it just updates its own policy based on that transition. Whereas if we see on SAC, SAC performs action, it observes the world, and then it remembers the action and transition. So it's like how memory in human brain works. During training, it recalls some of those memories and then try to improve on its current policy. Yeah, so that's one future direction that we're going to head on. And then SAC also has some technical advancements on exploration policies that we're not going to touch on today. Yeah, but that's our plan for the future.
But then if you add the memory, then you are going to sacrifice the parallelization.
Yes.
Right, because if you have the memory, then
You're going to sacrifice what?
so when you train the reinforcement learning, when you have memory, usually you have to sacrifice two things. Number one is parallelization.
Oh, right.
So that's number one. Number two is that if you have the memory, then in the engineering wise, the memory sits in the CPU. So then you're going to increase in swapping memory flow between the CPU and GPU.
Yeah.
So that will further slow down the training. So people prefer the on policy version, not having the memory, because people were saying that GPUs are cheap. So they're sacrificing the memory by choosing to just have more and more agents just running on their own GPU cores. Then you can parallelize it. So SAC has its own drawbacks, unless there's some secret sauce that I don't know. But we can discuss after that. Yeah.
Okay, nice job, guys.
Great. Yeah, so in conclusions, for now, we are still improving on the full control. It learns to drive very fast, up to 200 miles per hour. However, it is hard for it to learn the brake while it is driving so fast. So we are still figuring out how to do the improvement for the convergence.
Is the RL version going to be deployed on any hardware test?
So this is entirely in simulation. Yeah.
But, so it is intended only to be in simulation.
Oh, we have a go-kart in Richmond Fuel Station. We could actually test this and see if the go-kart can drive around Richmond Fuel Station. So that would be fantastic. So there's another group doing the go-kart drive-by-wire modification. The optimal solution is that we can achieve that to drive around Richmond Fuel Station fully autonomously in the summer. So that's what the students are committed to do. Yeah, but that's even longer.
Given that this is in Carla, we can also connect our tools to this. I mean, tools already interface to Carla.
Yeah.
In fact, they are part of the official Carla release as well.
Yeah.
But I think it's not just about testing and verification. It's also about training. So we had a paper last year where we showed that we can speed up RL training using CLink. So I can happy to.
Yeah.
That's another thing that we.
Yeah, absolutely. Yeah.
That would be very good.
Yeah.
So that's also very much in the spirit
Yeah.
of this program. Yeah.
See, I think we should. The consensus is that if we can represent rules in a more efficient way, differentiable way, I think that would be really a breakthrough.
Yeah. Hey, just for your racing, you guys should take a trip to Monza. I mean, there's no sense handicapping yourself,
Yeah.
Go collect it. Invest some money.
Yeah.
Go.
Yeah. We'll talk to Gary.
Sorry,
Yes.
you guys better go.
Yeah. Okay.
Yeah, thank you. Thank you, guys.
Thank you, guys.
Yeah. Thank you.